Well, here we go again. Now that the hard part of the course is over, meaning the part that has more concepts, more fundamental questions, now it's time to talk a bit about applications of those ideas to daily things. Today we're talking about detectors, especially radiation detectors. So, what is a radiation detector essentially? It's a device that somehow registers the passage of radiation, right? It may be several things. It may give you an image of that radiation. It may give you a count of how much radiation you had. It may be more specific and tell you which radiation it was, and it may be even more specific and tell you which energy that the radiation had. But let's start by the basics. A good analogy for me is light detectors, like your eyes, for instance, right? Your eyes are excellent light detectors. Film in a photographic machine, or a photoelectric cell, like in an elevator or something. The digital camera sensor, the CCD inside your cell phone, and so on. So detectors, these are detectors for light, for visible light. Now, let's use this analogy a bit further to understand what are the requirements for a good radiation detector. So essentially, radiation detector is something that interacts with the radiation, right? It has to interact with the radiation, otherwise you won't have anything to register, and then somehow transforms it into some usable information. So, simply putting, a detector must, first of all, allow the radiation to reach the sensitive volume. It is the equivalent of opening your eye, right, or removing your hands from your eyes. This seems obvious, but it's not. Let's remember, for instance, alpha particles, which interact very strongly with very thin solid matter. It's essentially clear that if you want to detect alpha particles, you can't have just anything between the source and the detector, right? That's why alpha detection is usually performed in vacuum, right, to open the eye. Then there's the second part. The detector must be able to interact with that radiation, meaning to see the radiation. Just think of, light is an electromagnetic wave, right? And we see it, but we don't see radio waves. We don't see microwaves, because our eyes, the sensors in our eyes are tuned to a certain, quite narrow range of frequencies, right? And we don't see charged particles either. So it's only electromagnetic waves in a very specific range. Detectors are usually the same. If you want to detect something, you must have a detector whose sensitive volume interacts with the radiation, right? So that's essentially an idea. Then you have to remember interaction of radiation with matter to remember, okay, if I want this, I need a higher Z, or anything goes, or for neutrons we have to do something that interacts with neutrons, and so on. Then, last but not least, you have to transform this in useful information, because see, we all know that radiation is bad for our bodies, right? It means radiation reaches the sensitive volume, meaning us, and the body interacts with the radiation. But we do not transform that in useful information. So we don't see radiation. We go all the way to seeing it, but the last step, that would be to transform that damage in some useful information, we don't do. Right? So that's important too, that you can somehow collect that information about the interaction and take it to your computer or to a display or something. First detectors obviously didn't use electronics because we were talking about the start of electricity. Electronics were not invented at that point. So there was essentially few detectors they used. There's the cloud chamber where you have water, which is kept in liquid form, but it's on the verge of becoming a gas, right? It's in low pressure. Then every time radiation passes, you form droplets of gas. And then you see a track of gas, right? Then there's the bubble chamber, which is essentially the opposite thing. You have gas, and when no, sorry, it's the opposite. Oh, it's something. Okay, but in either of these cases, we're talking about things that leave visible marks on a sensitive volume, right? Then we have scintillators, which are essentially materials in which the passage of light will produce both. The passage of radiation produces light, visible light. And finally, we have emulsion films, right? We all know about it. It's photographic film, and we all know that, for instance, this was one of the first detectors used by Röntgen when he discovered X-rays, right? We all saw the X-ray of Bertha's hand with the ring, so you can use, for some radiations, you can use films too, right? Or sensitive plates. They have plates covered with silver compounds. I forget which is silver oxide or something, which also registers passage of radiation. So this is a cloud chamber, just so you can see. And then this, what happens here? We have radiation coming from this side, left side here, and we have a magnetic field here. So by the curvature of the tracks, you can determine something like the ratio between the mass and velocity of the particles, and if they turn to one side or the other, you can tell if they are positively charged or negatively charged. This is an old picture, but this kind of stuff, modernized as required by today's standards, it is still used in CERN, for instance, in very high energy colliders, and they use it essentially for this, to detect and see the tracks of particles and try to understand what are these particles because of the tracks. And if you follow some tracks, you see they disappear, so this means something happened here. There's a lot to understand from this, right? So we can see passage of radiation here. Well, some fundamental characteristics of detectors. First of all is the sensitivity. To what radiation is it sensitive? Is it sensitive for alpha, beta, gamma, neutrons? What? Second, also maybe it's sensitive to one radiation if it is in a certain energy range, right? Like our eyes with visible light, right? Then there's the other question: can it discriminate between distinct radiations? Meaning, if I see or count or whatever events on a detector like this, if it's sensitive to more than one radiation, can I tell if this event was caused by gamma, beta, or photons or neutrons? And then there's the question of efficiency. Efficiency meaning, how much does it measure? If I had 100 radiations, whatever, 100 particles inside in the detector, how many registers would I have? Would it be 100 or 100% efficiency? Can happen, yeah, it can. Or was it 1 in 100? That's also something that happens very often, right? For photons, 1% efficiency is not a bad thing. Then there's the question of energy resolution, right? Meaning, can I discriminate between two distinct energies? And how well can I distinguish, right? If I had, I don't know, 1.1 MeV and 1.3 MeV photons, will I be able to separate them? Will I have a blur? In fact, we have detectors that will somehow overlap these two, and there's detectors that can even distinguish between 1.173 MeV and 1.180 MeV. So you see, energy resolution goes all the way. That's more important surely for monoenergetic particles. Then there's questions that are less related to physics and more related to the way you use the detector, right? Do you need the detector to be robust? So meaning first of all, okay, should it be heavy lift? We're saying, okay, we have badges that measure radiation in our lab coats. They cannot weight 1 kilo. If they weigh 1 kilo, we cannot use them, right? So, and then there's the fact, okay, I need to take this detector to places. Can I take this detector to places? How can I take it to, or this is something that's important too, right? And there's all kinds of questions, right? Sometimes you need a very small detector, sometimes you need a very large detector. And another question that sometimes arises, do you need immediate response? When you're talking, for instance, monitor in an area, you want to know if there's radiation there. Sure, you need it to be immediate. Like you're in a lab, you want to see if your hands are contaminated or something. You need the answer to be given to you at that point. Now, sometimes let's take our badges, for example. We use them the whole month and we only deliver them to be read once a month because we know, because the places we work are all well monitored. So that's just to see if on the average during the month we were okay. We don't need it to be immediate, right? And we don't want it to be immediate sometimes because the longer you expose a detector to radiation, best will be your response, right? Your detection level will go lower and lower as longer as you expose it. So, one very important thing, as far as I can tell, there's no detector that is sensitive to all kinds of radiation in all energies, right? Because the sensitivity will depend on the cross-section of the interaction of radiation with the detector. Meaning, for instance, if we want to remember that for photons we had, for instance, for photoelectric effect, it went with atomic number to the 5th power. So we need high Z, right? Otherwise we'll have just a lot of Compton effects. Maybe we won't be able to register what we want. It depends on the mass and geometry of the detector, right? A large detector will detect more radiation. A detector that covers usually if you think of a detector here, you have a detector here and you put a source here, you already lost half of your events, right? Because it's being emitted in all directions and only half of these directions take you into the detector, right? Imagine this is the source. If I put the source here, every radiation being emitted up and to the sides will not reach the detector. There are detectors which cover the source in 4 pi, and there are also there's intrinsic noise thing. It doesn't seem too important, but if you try to take a photo at night with a cell phone, this was more true up to 5 years ago. Now 2 years ago, now they put artificial intelligence and all that working on phone cameras, and that's also an example of what can do. Sometimes you can get rid of noise by post-processing, right? Getting your registers and doing some math with it to get rid of noise. But if you remember, if you take a photo in the dark, you have spots and you have a lot of noise that comes up. If you want to see something, you get your very dark photo, and you try to enlighten it, give it more light, and you will see lots of noise and weird spots coming on. Right? Detectors are the same. So detectors, every electronic equipment has intrinsic noise. Every device, in fact, even our eyes have intrinsic noise. So we need to know if our events will be above this threshold, this noise. Otherwise, you will miss your events in noise, right? Think about you talking to someone in a quiet room or in a very loud environment. I'm sure it has happened to you that you're talking to someone and you're not listening to half of what he's saying because the place is too crowded, too noisy, right? For detectors, it's the same. In a noisier environment, you need to talk louder. In a noisier system, you need to have larger pulses if you want to detect them, right? And last but not least, you need to think about the encapsulation of your detector. Sometimes you need to protect. Some detectors you can expose, but mostly we have our detectors protected by something, and this protection will absorb part of this radiation. Remember, alpha particles, they will stop at anything, right? And just a quick thing here, you see, in this class I'm more interested in showing you how much all the things we've learned so far have to do with, for instance, choosing the right detector, right? And how detection has to do with interaction of radiation with matter, with all the things we have said before. Okay? So, discrimination of energies. Discrimination of different types of radiation. In general, it's extremely difficult. In some cases, it's impossible. But we have a few solutions, right? The first solution, with modern electronics, we can digitize the pulse. You have the pulse that leaves the detector, and you can see by the shape sometimes, or by the amplitude, you can distinguish if it was one radiation or the other, right? But that's something you have to test, and it's never 100% good, right? But can be done. The other thing we can do is combine detectors and shields. Use the shields, use the fact that some things shield some radiation to your benefit, right? So for instance, in badges we can do that to distinguish between neutrons and gammas. So first of all, other thing, how does discrimination in energy work? For you to discriminate between two events with different energy, you first have to measure the total energy of the incident radiation, right? So you depend on the total absorption of the. So for instance, if we're talking gamma rays, you must make sure you either had a photoelectric. The best thing is a photoelectric event, right? Because then all of the energy of that radiation was deposited inside the crystal. If we're talking alpha particles or beta particles, you must make sure that the detector is thicker than the range of that radiation, because otherwise part of that radiation will escape, and if it escapes, then you lost some part of the information, right? If, say, this is my detector, and let's say we have some radiation here coming in here that have this range, most of these particles will exit the other side of the detector and will leave part of its energy outside the detector. meaning the detector will not be able to see the whole energy of the radiation. Now there's another type of radiation that has this path, this one, this range. This one will be fully collected inside the detector, and then you will have the knowledge about the whole energy deposit of the radiation, right? And essentially, usually for most detectors, the dependence on here, what we call canal or channel, is just a digital number from 1 to 4096, right? Just a digit, because we digitize events, so it's just the digital channel. It was meaning here this here is proportional to the size of the event, intensity to the size of the pulse that reached the detector, right? And here is the energy of the radiation. You see, usually energy, you can use a linear function to represent this dependence on the size of the pulse versus the energy. Sometimes if your energy range is too high, maybe you will need a second degree function. In some detectors you may need that too, but mostly we use a linear function and it's okay. Then there's the case of efficiency. Efficiency is now you want to translate what you measured to the intensity of the radiation, meaning I got here 100 events. Does it mean that I had 100 radiations, 100 particles reaching me, or does it mean we had 1000 and then that's why I registered 100 or more than that? So this is essentially depends on the type of radiation. If you remember the intensity, I told you that the alpha particles interact very strongly with matter in a very short path. So for alpha detectors, this can be very close to 1 or to 100% if you want. For beta particles, provided that the detector is large enough, yes, this can be true too. Not always, but it can be true. But then, for gamma rays, it's never true. You're always well below that. For instance, this here, I show you down here, is typical efficiency curve for a germanium detector, meaning it's a gamma ray detector, and you see it has a characteristic shape, right? So the best we can do in this case is like 1%, right? This was a small detector. Sometimes we can get better than 1%, okay, but not too much, maybe 4%. And what we have here, for instance, for lower energies, the gamma ray, it will interact with the encapsulation of the detector, which is aluminum, quite thick because the detector is fragile, and then it won't reach the detector because it stops on the aluminum in front of the crystal, right? Then, of course, now all photons start to come, and then it's okay. But as you remember, the dependence of the interaction, it decreases the intensity of any interaction decreases with the energy, and quite strongly. Then what happens from here on is that the radiation starts to pass through the detector without even leaving some register there. So you see, it has a characteristic shape because at low energies the radiation cannot reach the detector, and for higher energies it sometimes passes through and leaves no trace, right? So you see, it's very energy dependent, right? Here we are about 1 part in for 1.3 MeV, that's the case here, 1.4. We are about 0.1%. For 100 keV, you're almost to 1%. So there's a factor of 10 in this quite narrow range of energy, right? And if you go down here, it's even worse. So the other thing we talked about, energy resolution, is a measure of how precise is the determination of energy. It will depend on the way the signal is formed, on the type of the detector, on the type of the radiation, and also on the energy, right? Because larger energies you usually have worse resolution. But if we take a look here, we have two distinct detectors. The black line here is a germanium detector, which is known for its very high resolution. And in red, it is a sodium iodide detector, which is a detector known for being cheap and for performing well in several situations, but it's not so good in terms of efficiency of resolution. It has greater efficiency, in fact, than the germanium usually. And here you see, with the germanium detector, you see that you can determine these two energies, and that's those two I told before: 1173 and 1332, 1332 keV. They are emissions from a very used gamma source. We use it for calibration purposes all the time. It's cobalt 60. So you see here the difference, right? While for the sodium iodide there is a small superposition on these two radiations. Remember, 1173, 1332, 200 keV difference, less than that. But you can see some superposition here. And when we talk about germanium, no superposition at all. You could see much better than this, right? And for instance, these other events here, they are lost here. You cannot see them. Here another example, same comparison between two detectors. You see the two strong peaks from cobalt 60. You see they are somewhat superposed, but you can separate both when talking about the sodium iodide detector. With a germanium, you can not only see those two, but several things that were between them, and several others. For instance, here you have a bump. You would say, okay, I have one radiation here. No, we have at least two, right? And others that were completely lost in the sodium iodide, meaning that if you want a high resolution gamma ray detection, you need a germanium detector. You cannot use a sodium iodide. But for several uses, the sodium iodide is very good, right? So now talking a bit about what are these detectors. The simpler case, but still very used and very useful, are the gas detectors. Gas detectors are essentially gases. You have a volume of gas where radiation will produce ionization, and then somehow you will collect this ionization, right? The good thing is, in a gas, the ions and the electrons, because if you produce ionization, you will produce an electron and an ion. They are easy to collect because you just put some potential here, some electric potential, and you will collect all those gases. And there's several types like ionization chamber, proportional counter, Geiger-Miller, and others. They are essentially like this. You have here a canister with gas inside, right? In this case, the gas is circulating, it's entering here, leaving here. Sometimes you have it sealed. But what happens, you have here, each time radiation comes in, it will produce a photoelectron, right? You have an ionization, and then you have an anode here. The whole part on the external part is positive, so you will collect electrons, and you will collect electrons on one side and the heavier the ions on the other side, and you have now a current or pulses depending on how you do that, right? And if you think about it, if we start to increase this potential here, you start to accelerate this electron and these ions. And if these electrons get enough energy, they will start to be able to do secondary ionization. So if you had one electron, if you accelerate it enough, it will be able to do a secondary ionization. And then you have the opportunity to have tertiary ionizations and so on, depending on how much is the tension here. So if we take a look, if we have no potential, no electric potential, you will not see anything because you cannot collect the ions, right? You start to, here is the voltage. You start to turn up the voltage and you start to see something, but it's not everything because some of these electrons are recombining with ions in the material, right? They're so slow that they can recombine. And then you reach a critical point where essentially every charge is collected. Every charge leaves one charge. Every particle will leave one charge on the every particle that interacts with the medium, right? Because some will not. But every particle that reaches the detector and causes an ionization will be collected. But there's no multiplications yet. This is what we call ionization chamber, right? Then we start to increase even more, and you start to have the multiplication, as I told you, right? Electrons can now, electrons produced by ionization in the medium, they can ionize other electrons and other atoms and so forth. This is called a proportional counter, right? Because now in this place here, the size of the amount of charge you produce is still proportional to the charge that was deposited in the first place. So you do not lose the information about you do not lose information about the energy of the event. Then if you increase it too much, you start to have weird things happening. There's still some dependence between charge that is produced in the end and the number of ionizations in the first place, but it's not linear anymore because several things are happening. Sometimes the ions themselves start to mitigate part of that because you have a lot of charge reaching the anode, and then you start to lose efficiency because your effective field will be lower, right? So you lose proportionality. So this is a range we often do not use. And then if you turn up enough, you have saturation. Now every pulse, no matter if it is weak or if it's strong, will be amplified to the exact same place, because then it's just the dynamics of charges within the detector that say what happens. And you have essentially large pulses all the time, no matter if you had a weak or a strong event. That's what we call the Geiger-Miller region, right? That's the region in which Geiger-Miller counters work. And well, if you keep on increasing, now you just, at some point, the gas is not able to take that voltage anymore, and you just have discharge, electrical discharge continuous, and your detector is over. So, going from the lowest one to the highest one. Ionizations chamber. We usually, let's start by the end. The output current is very, very slow. So you usually need a very precise electrometer. We're talking pico amperes here, right? But there's good things about it also, because it's very hard to measure a current there so low. But there's one good thing: it works in current mode, meaning you do not try to see pulses, but you just try to see the current generated. And that's very good when you have very large doses, very large signal. So if you are in a very intense gamma ray field or in a very intense radiation field, detectors that will work in pulse mode, meaning they generate every time a radiation interacts with the detector, you generate a pulse, they will start to overlap pulses, and then it gets harder and harder to know the actual size of each pulse, how many pulses were. You will count two pulses as one, That's what we call dead time. Uh, in this case, as it works in current mode, there's no such thing. If you double the amount of radiation, you double the current it generates. So you have no problems with those things, and that's why it's usually used in dosimetry in medical physics, because we're talking very strong radiation fields, and metrology, because sometimes you need very, very high precision in some things, right? And gas is usually air, just because of the use in dosimetry, because if you use air, that's the definition of exposition. You will see that in radiation protection, but exposition is essentially the number of charges of charges that you produce in a given volume of air. Then we increase the voltage and we go to the proportional counters. Okay, this works in pulse mode, meaning every individual event will produce an individual pulse, right? So you have pulses now, and now you have to count pulses to count the amount of radiation that entered. And the size of the pulse, the height of the pulse, will give you the information about the energy of each individual event. They are largely employed because their response is proportional to the energy. They are essentially cheap. We usually use noble gases because we want to have high voltage, and we don't want the gas to steal electrons from the signal, right? And noble gases are known for being quite inert in that case. As I showed you in that picture, they can be of continuous flux, meaning you keep just circulating gas there, or they can be sealed and then they have a limited time span, because sometimes the gas will be quotes, burned. You will damage too much the gas. There's no more way to do, right? So the most used gas, we call it P10, is argon with a bit of methane. The methane has an important thing. It just avoids the detector from oversaturating. Then we start giving even more tension and voltage, and then we come to the Geiger-Miller. The Geiger-Miller, the signal is not proportional to energy. It's signal here, or to the type of radiation. It's only sensitive to the amount of radiation. If you remember the figure here, just go back a bit. You see that we had alpha particles here and betas. You see the signal in this region is exactly the same, no matter if it was an alpha, a beta, or a gamma particle. Meaning it works in pulse mode, meaning it's only good for counting radiation. It will not you will not be able to tell which radiation it was, but you will know it was radiation, right? What's good about it? Is that it's very sensitive. The cost is minimal, because there's no point in putting complex electronics in this, because signal is so large that sometimes you only use a speaker, right? You may all have seen those detectors that go. It's just the signal of the detector being fed into a typical speaker. You can also use some electronics just to count these, but so they are very sensitive, but the dead time is large, because the whole process is so, every time a radiation reaches there, it causes ionizations and secondary ionizations up to quaternary ionizations, and then the whole detector gets if you can imagine, you produce so much charge that the detector is, at some point, the charge there just cancels out the external electric field, and the detector is blind, and then things start to recombine and you're able to see another event. So it's very good for just, essentially for what we use. Is there radiation here or not? and they are very sensitive, so they're not to be used in very large radiation fields, very strong radiation fields. They're very useful for weaker ones, for if you want to see, okay, is there anything here? But that's the most used one. We use it everywhere in the lab. Well, there's also different kinds of detectors, like for instance track detectors. In those detectors, as radiation passes through an insulator, right, and it has to be a material where charges are not allowed to circulate freely. What happens? It causes ionizations, right? And after ionizations have happened, there's some electrostatic displacement, because now you have positive charges that will repel each other, and we have now a very damaged part here on our system. That may be ceramics, maybe glass, maybe even human teeth, human bones, or plastics like CR39. And then you can, for instance, do a chemical etching of that, and you see the bulk of the detector here is still good, and this one is very damaged. So if you attack it with a chemical agent, usually we usually use sodium oxide, hydroxide, potassium hydroxide, sodium hydroxide. It will attack this damaged region much more than the rest. And if you look at the microscope, that's what you see. These are what we call tracks that were left by radiation. There's also scintillators. Scintillators are materials in which radiation somehow causes the emission of light, and then you somehow collect this light and you have a signal. Usually we have a scintillator and then some type of material that will, some type of device that will turn this scintillation, this light, into an electric pulse. Right, this was the old thing we used called photomultipliers. They relied on essentially the same idea you have in a gas detector, right? You have the electron is accelerated, you produce an electron, then it's accelerated and then collides with a plate, produces more electrons and more electrons and more electrons, so the signal gets stronger. Nowadays we have solid state devices that can do the same essentially. But essentially that's the idea. You produce light and somehow you convert this light into an electrical signal. And there's essentially two types. You have the inorganic ones, which are essentially crystals, right? Like sodium iodide, cesium iodide, bismuth germanate. I don't know how to say this in English, but it's called BGO. You have barium fluoride and others. These are inorganic, meaning they are crystals, and the event takes place in a way. And on the organic ones, that can be liquid or plastic or even a crystal, the way the light is produced is different. But in both cases, you have light produced when you have radiation. In the inorganic ones, the idea is simple. Radiation comes in, it deposits energy on one electron on the valence band, taking it to the conduction band. And then it doesn't fall back directly, otherwise it would only give you the energy back, but it passes through intermediate levels, which will, in its turn, instead of emitting X-rays when decaying, it will emit light radiation, right? And in the organic ones, essentially, the radiation causes a whole molecule to be excited, and then usually vibrations. And then when the molecule starts to come back to the fundamental state, it emits back the energy in the form of visible light, right? So, usually especially for the inorganic detectors, you see, when I talked about inorganic, we said iode, cesium, bismuth, right, barium, everything very high Z, meaning it has very high efficiency for gamma rays, for instance. but they can be used for gamma, beta, alpha, and even neutrons. Because of the way this whole thing happens, the response is very fast. Sometimes you want to know not really the energy of the radiation, but you need to be very precise on the time when it happened, that interaction happened. And scintillators are very good for it because their response is in the nanosecond scale. They're cheap, but their resolution is not the best, right? And some things that are quite obvious, but if you think, okay, the most important thing here, right? The detector must be transparent to its own light. It seems obvious, but it's not, right? Sometimes the detector will absorb part of the light it emits, right? Because of the structure. This is especially true for the organic ones, because often you have the same the excitation you have can be replaced by an excitation in the next molecule, and then what happens? The emission you gave will be absorbed by the next one. So that's something you must be careful. And luminescence must be short-lived. Now there's a catch here, because we want, of course, the luminescence, meaning the process of emission of light, to be very fast, right? So that we have the fast response they are known for, and so that we have instant response. But there are cases in which we want the exact opposite of that. Let's go back to our radiation badges. In our radiation badges, essentially, we have scintillators. Like it's lithium fluoride. And lithium fluoride has a very unique characteristic. When it's not really unique, but it's very useful for us. There's more elements that have that. But when you have the interaction, the electrons are promoted to excited states, but they are trapped there. So you do not have immediate emission of light. You just go on piling up those excitations which are frozen in there. And then once you heat this detector, if you heat this crystal, then vibrations make these electrons be able to come back to their fundamental state, so the light is all emitted only when you heat them. And so that's how they work. You spend a month with the badge in your lab coat, and radiation is piling up there, the damage is caused by radiation, and in the end of the month they put it's some kind of oven with a light sensor. So once you heat it, you will have light emitted, and then you can count the amount of radiation that you were exposed to during the whole month, right? This is called TLD, thermoluminescent detector, for this reason, right? So, but you may know scintillators from, let's say, when you're doing a tomography. In a tomography, you will be exposed to a scintillator. The detector used in tomographers are scintillators, because you don't require the whole best energy resolution. You need efficiency, and you need it not to be that expensive. They are expensive, but imagine if we used an even more expensive detector within it, right? So scintillators, old things they used called gamma cameras, were the predecessor of these tomographers. They also used scintillators, right? And this is, if you take a look, this is one of those when you open it, right? You have here an X-ray source, and you have here the sensitive part, which is essentially a large scintillator with several electronics here to know where you can make this position sensitive by knowing where did the radiation inside. So you do that and you make images with it, right? So that's an X-ray machine here, and here a large scintillator with very small. You have a lot of light sensors here to get where the scintillation was happened. If it happened here, here, or here. Now, there's also the semiconductors. Semiconductor, if you take the definition, is essentially an insulant that may become a conductor. Meaning what? You have here, in an insulator, you have the conduction band and the valence band and a very large gap here, like 6 electron volts or something. So you cannot it's very hard to promote an electron from the valence band to the conduction band, and that's why it is an insulator, right? You do not have free electrons. In a metal or conductor, it's the opposite. The valence band and the conduction band, they overlap, and so there are quite a lot of electrons here which are free. So if you put some potential here, they can go wherever they want. Semiconductor has a conduction band and a valence band, but a much smaller gap, more than 10 times smaller than the worst insulant you have. So that it's quite easy to promote electrons in the right situations, right? When we use semiconductors in electronics, what we have happen, we just increase the potential, and if the potential is large enough, you will start to, so they are insulators, but at higher potentials, they become conductors, right? In our case, it's different. When radiation passes, they promote electrons to the conduction band, and then you have free electrons, but only when radiation produces them, right? So in the old days, we could not control that well the amount of impurities that you have inside your crystal. And that's a problem because then you don't really know the gap. There are spurious levels here, and sometimes you cannot control that. So what we used to do is to use a dopant, right? There's still some detectors where we need it. We put something to create our own levels there, which are expected and will not harm the way the detector works. Nowadays, nowadays we have, for instance, for germanium, we have reached a level of purification where that's not needed anymore. And so that's the idea. We have here a semiconductor, and then you apply some potential here, and you have, the greater is the field, the more you just leave a larger part of the detector, what we call depleted. Depleted meaning there's no free electrons here anymore, right? So this is a part where there's no charge, no net charge, and then when radiation passes through this part, the depleted region, you will produce electron pairs, and then we will collect these electron pairs, and you will have, right, some kind of signal. So the advantages, the energy resolution is absolutely incomparable. It's much, much better than any other detector we have. At least the regular types. There are very specific types of detectors used for very specific stuff that have better resolution, but they're a nightmare to work in any other sense, right? And they can be used both for charged particles and for photons, provided you use them correctly. The main disadvantage, especially of the inorganic ones, is their crystals, meaning they're fragile, right? There are all crystal ones, there are only inorganic ones, and they are very fragile. They have very low efficiency, especially for X-rays and gamma rays. The output signal is very low. For gamma rays, we are talking essentially the signal that leaves the detector is in the nanovolt scale. So it's very, very small. It's very, very hard to properly separate it from internal noise. So we most times especially for gamma rays and X-rays, it will require refrigeration at minus 200 Celsius. This is liquid nitrogen temperature. And we also use this to refrigerate the amplifier, the first amplification stage, so that we can have, because when you drop the temperature, you also drop the noise, right? Because electrons will oscillate. Temperature is a measurement of the oscillation of electrons and of matter, right? So lower temperatures mean smaller oscillations, which mean much smaller noise. So we have to refrigerate, because otherwise, for instance, we apply the high voltage, your semiconductor would become a conductor, and we don't want that, right? We cannot detect anything in a conductor. So you freeze it, because then you have when you freeze it, you can apply very high voltage without turning it into a conductor. And at the same time, you can decrease a lot the noise for the first amplification stage. Most used semiconductor detector, at least for us here, is the germanium detector. We call it that. Most people call it HPG. Depending on the era, it will mean hyper pure germanium or high purity germanium. First years they called it hyper pure, now they call it high purity. Well, the detection of radiation requires large volumes. Remember, gamma radiation is very hard to stop, right? And high atomic number. Well, that's an issue, because semiconductors are usually you have very few elements you can choose, right? The main ones being silicon and germanium. In this case, we must use germanium because its atomic number is 32 against 14 of the germanium, of the silicon. And it is possible to produce very pure samples in very large amounts. So that's good. That's what we need. The low gap implies that the leak current, the low gap meaning the gap between the valence band and the current band, is very small. And so you do have to keep it refrigerated, because otherwise at room temperature you would have it turned into a conductor. Now that's an interesting thing. I don't know if that's still true, but for many years germanium, because of these applications and other very sensitive electronics applications, they developed ways to purify germanium that were better than what they could purify any other thing in here. So we can have, for a detector, we're usually talking about 10 to the 9th atoms per cubic centimeter. This means 1 part in 100 trillion. Yeah, you just let it sink in. It's 1 part in 100 trillion. So for each 100 trillion germanium atoms, you can have 1 atom that's not germanium, right? So there you see, it will be expensive, right? And because of that, you do not require those dopants. The energy resolution is very, very good. I'll see. You've seen before, and I'll show again later. So that's essentially how it works. The most used geometry is this coaxial one, we call, because if we start to create larger and larger crystals, say we have a crystal like this, right, and we apply the potential here and here, what happens? It's a long way for the signal to process. Imagine if the event can happen up here or down here. It's in either way, something will have to travel a long way inside the crystal, and this means more chances of this event being recaptured and you have no signal. And more than that, if you think of essentially this is a very large condenser, right? A very large capacitor. And if you think two small plates here and a big crystal inside, the lines, the field lines here will be too distorted. The field will not be equivalent in the size and in the middle. That's why they came up with this idea, right? It's just, imagine you had this, but you have a hole in the middle here, and you apply tension from here to here. And then when you do that, you have a much more constant electric field, and as you see, any event will be happening close to one of the contacts. Well, we usually, when we talk about germanium detectors, we say, okay, this is a, when you purchase it, there's some numbers they give you, and they say, okay, this detector is 25% the efficiency. Efficiency of 25% means not that it 25% efficiency, as you would infer immediately. No, 25% efficiency means you have 25% of the efficiency of a 3-inch sodium iodide detector. Because when they were released, the standard best detector they had were these. So the idea is, how much is your efficiency related to that? So detectors can be of between 10% and even 200% efficiency. As I told you, 200% of these detectors, not 200% real efficiency. And a long while ago, we would say that the approximate cost was $1,000 per percent efficiency, meaning from $10,000 to $200,000. And now it's not that case anymore. It's a bit more expensive than that. Right? So we have to apply a few kilo electron volts in this crystal so that we will produce our signal. Right? And here is the difference. You see, here you have what a germanium detector is capable of, and here's a sodium iodide. And then you see why we have to pay all that money for one of these detectors, right? And just to make sure, now it's the truth. This is a true spectrum I collected in our lab with a cobalt-60 source. So you have these two gamma rays are from cobalt-60, right? As I told you, but you see there's more things here, and two of them are very interesting. Here there's a 1460, a peak at 1460 kilo electron volts. This is potassium 40. Remember I told you that potassium 40 is one of the primordial radionuclides. It's in everything, including our hands. So we handle the source, we handle things, and we start depositing potassium everywhere. So there's potassium. And there's also a small peak at 511 kilo electron volts. These two radiations, they are above 1022 kilo electron volts. That's what's needed for having pair production, right? This energy range, pair production is not dominant. It's still weak, but there is still some pair production happening. And then remember, when the positron annihilates, it produces a 500 kilo electron volt gamma, I mean 2 ones. And so you see, everything we've talked so far start to come up whenever we talk about. And then just to take, there's also the other semiconductor that's has a lot of use, is silicon. There is 2 ones. The silicon lithium detector is one we used for X-rays. We need the implantation, and then because of the implantation of lithium, there's a limit in size. We cannot produce as large ones as you want because the lithium would not implantate homogeneously. Right? It's using for X-rays. X-rays, not rays. Okay. And there's another silicon detector this one has a lot of use for many things. It's a surface barrier. It's silicon doped either with aluminum or gold. They're made very small, and they're very much used for alpha particles. They can be used for electrons too. It has very good resolution, right? And you can it's the best one. It's the best detector for alpha particle spectroscopy, right? If you want to see alpha particles you want to see the spectrum, if you want to know the energies of the alpha particles. Resolution is some 10 times worse than that of the germanium, but that has also to do with the way our alpha particles interact with everything. There's good stability, but they are light sensitive and they are very, very fragile because they have a very fine outer metal layer because you don't want it to block the alpha particles, right? And so if you touch it or anything touches it, it will be contaminated and you will start to have, you scratch it and the detector won't be good anymore, right? And because they are very, very small and we're using them especially with alpha particles that cause a lot of damage, these detectors usually have a short or shortish life. Because a germanium detector, we have some working here that are here for over 30 years and are still working as well as they were. For these ones, it won't happen because the alpha particles will cause too much damage and they start to lose their ability to detect radiation, right? Then, last but not least, neutrons. Neutrons, they have no charge, so as we just said in the last class, interaction is purely nuclear, and then you have to use some kind of converter to transform neutron into ionizing radiation. That could be an alpha particle, a proton, some recoil nuclei, right, if you have a collision and the nuclei recoils, some fission fragment if you have fission, or even gamma rays. So eventually what we do, we either use helium. Helium has a good cross-section, helium-3, for an NP reaction. Boron has a very high cross-section for this reaction, something like 3,000 barons, and you produce an alpha particle. And the lithium ion, both of them are very highly ionizing. Lithium-6 can also be used with an alpha reaction. It produces a tritium, and the alpha particle can be easily detected. Sometimes we have gas detectors with uranium deposited on the inside of it, so that you have fission, and then fission fragments, are very high energy. They have very high energy. They are all very highly charged, and you can detect it simply. There's something called recoil protons. If you think hydrogen, if you think high energy neutrons entering here, they can scatter, and in that case now you have a proton that's recoiling in high energy, and now it is a heavy charged particle, right? There's also, for several uses, we use gadolinium, because this has, in this case we're talking about 50,000 barns cross-section, giant cross-section, to produce gamma rays. And these gamma rays can be, you can just use a photographic plate, for instance, or something, to register these gamma rays, right? So neutron detectors are usually one of these types we seen before. Gas, in this case you use either you use boron on the gas or helium-3 on the gas, or you have a fission chamber, you use fissile material there. Sometimes you deposit boron on the inner layer of your gas detector. There can be plastic scintillators. Either they have some material there that has cross-section for neutrons, or you just use it for fast neutrons, because then you have the recoil proton. You can use liquid scintillators with a bit of gadolinium. There are scintillators which are inorganic, and then they have lithium, and then you have, with lithium, you have the cross-section for neutrons. Also, in our badges, in our radiation badges, you can have, it's, as I told you, it's lithium fluoride. So if you have it, it is sensitive to neutrons because of lithium-6, right? We can use traces. once again, either using boron to produce alpha particles, or the recoil protons for fast neutrons. Semiconductors, you have photodiodes where you spike them with lithium-6, and then you have sensitivity, and so on, so on, so on. Every kind of detector can be adapted to use for neutrons if you place some kind of material that will interact with the neutrons, producing a charged particle. The downside is there's no energy sensitivity, because they all rely on nuclear reactions, right? And because we rely on nuclear reactions, the energy released by these nuclear reactions is much greater than the energy of the neutron itself, and you have no idea anymore. There's people trying to use the recoil protons as a way to determine the energy of the neutron. I don't know if it will work. We hope it will, but that's the only way we could think of to try. Okay, and well, that's it. Essentially, the idea in this detectors class is not that you become a detector expert, is that you understand how everything we learned so far impacts when you try a thing so simple as detecting radiation. You need to understand how radiation interacts with matter. You need to understand several things about it. What to understand, you have to understand nuclear reactions. You have to understand a lot of stuff to be able to choose the best detector. Okay, so now the next classes will be on several applications we have for radiation and nuclear physics in general. I hope they will be more entertaining, and the idea there is the same one that was here. It's just to get you to see how much all those concepts we've learned so far can be used for several different things. Okay, bye bye, see you there.